Okay, so if we're adding bromine to an alkene, if we have excess, and again, we have to pay attention to the quantity that we have, then this is going to end up being our product, right? But in the case of a benzene ring, right, the addition of bromine, and then we also are going to have iron 3 bromide, we're going to end up with bromine being added as a substituent on the ring structure. So you still keep the benzene ring, but you're just adding bromine to a substituent structure. And then the other, the second bromine is going to be form hydrogen bromide or hydrobromic acid. So depending on whether it's an aqueous solution or not. So. Okay. So the first step is going to be the slow step. The second step is going to be the fast step. So let's see. Okay. So the double bond contributing its electrons to the nucleophile, right? I'm sorry, the electrophile. Then that's going to be our initial or slow step, and then the in this case the bromine or the contributing electrons, the base, the Lewis base, is then going to contribute its electrons to that hydrogen. That hydrogen is going to contribute it to restore that bond. And so then you're just going to get that substituent being added on directly to the ring structure. Okay. So, okay, so group ones, these guys are going to be nucleophiles. And then these nucleophiles, they're going to basically undergo electrophilic addition reactions. So in that case, we're going to be able to add on directly to those bonds, where in the case of the ring structure, that wasn't the case. We're getting the substitution added onto the aromatic ring. Okay. Questions, concerns, Cash? You're good? Okay. So at this point, we've established a lot of the reactions that we've done with alkenes, alkynes, dienes, right? And we also know what's happening with the benzene rings, right? And then we can also get the formation of those ring structures, right? The cyclo alkene structures, right? And you guys are familiar with that. So if it were me, I would take this opportunity, because we went over, like, I know within this chapter, there's at least 8 new reactions that we've gone over, at least 8, right? I would either pull out those flashcards with those 8 that we've gone over, so we know that those are the ones that we're going to be studying, right? And be familiar with them, okay? And I need to check to see if Mesa got the new slides. So chapter 9. So chapter 9 here, we're really going to talk about substitutions and elimination reactions. Now, the funny thing is that we've been exposed to substitution and elimination reactions already, but we weren't given the terminology yet, which I think is kind of weird. They wait till chapter 9 for the terminology. As you guys realize, I'm reading the book as we go along just as much as you guys are reading the book as we go along, because it's a new book. I haven't gone through it completely yet. So The first 8 chapters were dedicated to alkanes, alkenes, alkynes, and then we also know the cyclic cycloalkanes, alkenes, and the benzene ring. Okay, you've been sort of exposed to epoxies because that's one of the products that we get from the alkynes and alkenes, right? We've been we've been exposed to benzene rings, right? But just briefly, right? But again, we've primarily focused on the first group 1, essentially. Right? Okay, so now we're going to start focusing on group 2. And then in group 2, we're going to be focusing on the substitution. And again, we've talked about some of them already in terms of the reactions. Now we get the official names of some of the reactions. Okay, so let's start with, you guys have chapter 9? Everybody got a chapter 9? You guys will get it on Saturday. You guys are going to be here Saturday, right, Abby and Kayla? Are you guys there?
Yeah.
Okay. Okay. So these are group 2. So do you guys remember this group? Hydrocarbon and an X, what would that be? Where, you know, X stands for fluorine, chlorine, bromine, and iodine. What was it? So if we have a carbon chain, we always make reference to a carbon chain as what? If it's all single bonds, alkanes, okay? So if it's a side chain, then we call it what? So what do we call a side chain of a methyl, a meth group? Okay, so if it's a side chain of just general hydrocarbons, what would it be called? What is the change that we make to meth to make it a side chain? We add what? YL. So if I'm talking about generally the whole class of hydrocarbons that are all single bonded, I would say Achille halides, right? I may have misspelled that. Alkyl, Al, put the L in the wrong space. ALKYL, Achille halides. Achille halides. Okay, so we have our Achille halides. These guys are let me move the hydrocarbon and OH, an alcohol. Okay, this one you guys may not recall, may not remember, but we'll see. We have hydrocarbon, O hydrocarbon. We actually talked about this. What was it? Ether, that's right. Okay, we have a ring structure that's attached to an oxygen and R groups. You guys should know this one. Okay. Again, since we're assuming they're all single chains, we always going to start off with it's an epoxy. That's right. Achille epoxies. So Achille epoxides. Okay. It's not working. Okay, so if we had a C here and we didn't have this here, this would be called, say, if it was a carbon here instead of an S, it would be called an ester. Okay, so this guy is called sulfonate ester because you have that sulfate or a sulfate-like structure, sulfonate. And then we know that it's double bond and then a no, that's the ester component. This guy here is going to be called sulfononium salt. So this guy is going to be called a quaternary that might be spelled ammonium. And then hydroxide. Okay, so all of the compounds in the prior slide are all going to be electrophils. So if we take a look at this guy basically shows it. So if we have a halide, an alkaline halide structure, we know that the halide is going to get that partial negative charge, and then the carbon part is going to get partial positive, right? You guys remember that in terms of polarity. We know that this is going to be a polar bond because the halides are going to be much stronger than the carbon, particularly if we're working with fluorine, chlorine, or bromine. Bromine's kind of well, relatively close, but it'll be slightly polar if I remember correctly. But when you get down to iodine, that polarity doesn't exist, right? Okay. So in this case, these guys are going to be electronegative atoms, or they're going to have electron withdrawal. So this will be the group that we're going to be withdrawing the electrons from. Okay. And this group is also going to be attaching to an sp3 carbon. Okay, so when we look at this, we're going to have two things that are going to be able to happen. One is going to be a substitution, and one is going to be elimination. Okay. So because they're electrophiles, they're going to be reacting with nucleophiles. Okay. So in this case, the first case, a substitution is when the electronegative group is replaced by another group. We're substituting, right? Elimination is when we basically remove the electronegative group and then eliminate it along with a hydrogen, okay? So in other words, we're going to remove it completely. So elimination is when we're removing that group entirely, where substitution is just that we're going to replace one or another, okay? Okay, so the first group that we're going to be talking about is the Achille Halides. So Achille Halides are going to have, they're going to be basically a relatively good group for leaving, right? So, so in the case of the substitution reaction, here we have methyl bromide, and we're going to be substituting with an hydroxy. So in this case, we're just going to get a complete substitution where we just end up with methanol, and we end up with the bromine ion, or the bromide ion. Okay, so this case is called the substitution, right? It's going to be precise because you're substituting an electrophile for an electrophile, right? So it's going to go in the direct replacement. And then this is also going to be called a nucleophile substitution reaction. Because the atoms that are going to be replaced is going to be replacing a halogen is a nucleophile. So a nucleophile is replacing a nucleophile. Okay, so you guys remember kinetics, right? You don't remember the rate is equal to the rate constant times the concentration of your two products, or we could say not the products of the reactants. So it's just, let's go back real quick. So let's see. So let's say we have this reaction. Okay, so the rate of this reaction can be written two ways. It can be written as rate it can be equal to the rate constant times concentration of A. Actually, let me use different letters, otherwise I'm going to get myself in trouble. I'm really messing up today. Okay, so the rate of the reaction is going to be equal to the rate constant times the concentration of A to the X power times B to the Y power, where X and Y are going to, they determine the order of the rate reaction. So in other words, how fast it's going to be happening exponentially, right? And that's usually determined via experiment, okay? Well, they're the order. They're considered to the order of the reaction. And it kind of gives us, it lets us know how the reaction is going to behave, right? So if it's 1, right, then the speed of it isn't, it's like, I shouldn't say it's going to be big, but the speed is going to be less than if it was 2, right? And so usually if we talk about the order of a reaction, right, a lot of reactions that we work with, they're either going to be first order, meaning that they're going to be relying on this one, and they may not be relying on this one, meaning this is also to the first power, right? They could be second order, where we're relying on this one and relying on that one. So together, it's a 2-order reaction. Or they could be third order, right? Which is rare, but it does happen, right? And then beyond that, you typically don't have, right? Okay. So, and we kind of talked about that when we were in general chemistry. So when we talk about the kinetics of the reaction, so the kinetics is going to be approximately equal to the concentration of the alkyl halide and the concentration of the times the concentration of nucleophile, right? So in this case, it's just going to be a first order for this guy, for the alkyl halide, and it's also going to be a first order for the nucleophile, right? Basically meaning that they're going to have about equal contribution to each other, right? Okay, so this tells us, so the rate law basically tells us that the molecules involved are in the transitional state of the rate limiting step. So do you guys know what I mean by rate limiting step? Rate limiting step is the step that determines how fast the reaction goes. So if we take a reaction, we could have a couple of intermediates that are produced along the way, right? So you can say CD first becomes CD coming together, and then we get CD being broken down to A plus B, right? So that middle reaction is an intermediate, right? So the rate limiting step is the step that is the slowest of the two, because they're going to determine the rate. A reaction is only going to go as fast as its slowest step, right? So if you guys ever went shopping with a friend, and then this friend is really, really, really slow shopping, I hate going shopping for that reason, right? So where it would take you 10 minutes to go shopping, it takes them 2 hours to go shopping, right? So that's an example of a rate limiting step. That friend shops really, really slow. You shop fast, but you're not going to get out in 10 minutes because you know this friend that you go with takes 2 hours to shop. So that would be an example of a rate limiting step. Okay. So this reaction, because it's reliant on the two things, is going to be called substitution nucleophile bimolar, meaning 2 molecules, or bimolecular, not bimolar, bimolecular. Okay, so we often will call it abbreviated as SN2. And like I said, you guys have been doing this already. We just need to tell you the name, right? Okay, let's go. Let me clear. Okay, so if we looked at the, yeah. No. SN2 makes reference to the fact that you have two things that are contributing to the reaction, right? So you're relying on both the concentration of the nucleophile, and you're relying on the concentration of the alkaline halide, right? So it's two molecules that you're looking at, right? So in this case, both molecules are affecting the rate, right? So sometimes what happens is that second molecule isn't going to affect the rate, right? It's really just dependent on, let's say, you have a molecule that has to have a certain orientation, right? Even though you have this thing there, it has to have the right orientation. So it's not going to be dependent on this one. The rate isn't going to be dependent on this one at all. It's going to be solely dependent on this guy getting the right orientation to do it. So it's only dependent on one of them, right? So that would be unimolecular, right? Uni meaning one. And then that would be an SN1 reaction. Does that make sense? Even though you have two things that are reacting, but it's that one that's really important. Here we're saying both of these guys are important. So that's why we say bimolecular. Yes, it's always going to be an SN2. It's just the nature of the beast. So both of those are contributing. The concentration of both are going to be contributing, right? Because if you have too little of the first one, then this guy's going to slow down. If we have a lot of the first one and a little bit of the second one, well, we can compensate, but still, this guy's going to be dependent on it. So it's depending on both. Okay. Okay. So if we looked at the relative rates of the SN2 reaction, okay, so the methyl halides are going to be the most reactive. The first degree alkaline halides are going to be the next reactive. The second degree alkaline halides are going to be the third reaction. I mean, the third in terms of reactivity. And then the third degree is going to be the least. Okay. So what do I mean? So we know that this guy most reactive, right? First degree, basically meaning that you have okay. Second degree, meaning that you have more carbons added on, right? Okay. So, or you're getting branching of carbons, right? And so that's going to add on to it being less reactive, right? So the methyl, of course, making more sense. It's going to be very active with just that quick substitution. The more stuff you have, the more possibilities that you have other things affecting. Okay. So let's take a look. Clear. Do we have any extras so that I can make sure to put them in the back? Okay. Okay. Okay, so here we have a, let's see, what is this? 1, 2, 3, 4. So that is 2, 3, So that's 2-bromobutane. I guess I could just read what they have written there. And so we know that it's in the S configuration, right? So if we do the ordering, okay. And then by us adding an hydroxyl group, right? What happens is that we're going to end up with the inverse of this. So we're going to end up with an R configuration, okay? So if we have an asymmetric center, then we're going to always produce the inverse configuration when we do that substitution, okay? So we want to make note of that. Nice little chart. So if I start off with an S, I'm going to end up with an R. If I start out with an R, I'm going to end up with an S. It's always going to give me the inverse. Okay. So and also let's take a look. So this guy would be 1, 2. So is this a primary halide, or is it a secondary halide, or is it a tertiary halide? Primary would mean what? It is a secondary, right? Because it's coming off of the second carbon, right? So if it's coming off of any of those chains right there, it's going to be a secondary, right? If it was at the very end, primary. So primary basically means it's at one of the ends, okay? Tertiary, well, tertiary is when you have branching, and then it could be part of the branching, or it can be coming off the branching, okay? So that would be tertiary. Okay, so if we look at the relative rates, if the alkali is a primary halide, that's going to be faster than in the case of a secondary halide. And then also that's going to be, secondary halide is going to be faster than a tertiary halide, okay? And that's dealing with proximity, right? So if it's at the end, it's a lot easier to get to than if it's somewhere in the middle, right? And then if you have things that are branching off, it's harder to get to, right? So, okay, and then in all of those cases, we're going to get the inverse or the inverted orientation, right? So if it's an S, it's going to be an R, okay? So the mechanism, so we already know that the electrons are going to be donated by our nucleophile. Nucleophile is going to donate its electrons, and it's going to donate its electrons to, in this case, the methyl group. You need to get some sleep. You're not supposed to sleep in my class, you sleep at night. So maybe I should just have you look at the lectures at night to help you sleep. Okay. So then that's going to allow this bond to donate its electrons to there, freeing up the methyl group, making the bromide ion. And then we just get that attachment. Now, the fact that it attached from the other side, it attacks from the back side. That's what causes it to have that inverted orientation, right? So it's not attacking from this side where the bromine's at. So that's why you're not getting a direct replacement. So instead, you're getting it coming in from the other side. Does that make sense? Now, will you guys remember that? So we know that in the case of a substitution, we're going to get attacking from the backhand side. So just kind of think of it as like a shady person. They're going to attack you from the back rather than take you head on, right? That's for SN2, right? Yeah. Okay. So why do you attack from the backside? Well, we already know that. I mean, it boils down to energy, right? That's what it really boils down to. So if we're attacking from the backhand side, it's less energy, right? So if our nucleophile here, it's going to be in phase with that carbon, right? Less energy. If I try to attack from the front side, then I have two things to contend with. I have one thing that's out of phase and I have one thing that's in phase, right? More work for me. I'm not going to do that. Okay, so here, less work. It's a lot easier to attack just that carbon from this side, right? And then rather than messing with this guy entirely, that's out of phase. This carbon that would be out of phase on this side, but this guy would be in phase. Okay, why bimolar? Bimolecular. Okay, so we know that that's because we have the bromine breaks a bond with the carbon, and then the OH is going to be forming with the carbon, and so your transition is going to have both of the molecules existing at the transition state. Okay. So, and then in this case, this guy's going to be partial negative, and this guy's going to be partial negative, and that carbon is going to be partial positive. Okay. Are you leaving at 5 or are you leaving before 5? Okay. So why do the methyl halides react faster than the tertiary react slower? Okay, so our methyl halides are basically going to react faster. We kind of talked about this earlier. You're not going to have as much to deal with. You're directly targeted. You have right there is a single line of attack. This here, this is a, so again, this would be a second degree. Okay, so in this case, you have a lot more to sit there and deal with. Okay, which side am I gonna go work on, right? So am I gonna attack on this side here, or am I gonna attack on this side? You have decisions to make, right? More work. Have you guys ever, again, we're gonna take the shopping analogy. So you go in shopping, you wanna get cereal, right? Now, if there's 100 different types of cereal, you're gonna take more time to pick out the cereal that you want, especially if you don't have an idea what cereal you like, right? Compared to if there's one type of cereal, what are you gonna, it's gonna go pretty fast, right? So in this case, you only have one type of cereal, right? You don't have any choices. Here, oops. In this case, I have options. Oh, if I go here first, what's gonna happen? Oh, if I go, so in other words, I first have to find the right point to react in this case, right? Again, I'm going to be attacking from the backhand side. I'm going to be attacking from this point, but I have to get oriented right. So it's going to take longer for me to get oriented right to find that spot, right? Then if I have 3 carbons, right, that's going to make it even harder, right? Because again, I need to find that center carbon to sit there and interact. Well, these 2 guys are going to kind of get in the way, right? And then if I have a ternary carbon halide, that makes it even worse. Okay. So does that make sense? This is a secondary, right? Ternary. Okay. So, and then if we look at it again, steric hindrance. The more stuff you get in the way, the longer it takes you to find the right spot for you to react. So another analogy, you're at a nightclub. You have a girl that's hanging out, let's say you're a guy, and you have a girl that's hanging out with all of her girlfriends, right? So all of her girlfriends are going to act as steric hindrance, right? They're going to keep you from getting to the one that you want to get to, because that's what they do when they get in groups, right? They're like, you know, we came here together, we're going to leave here together and stuff like that. So you want to go and ask her to dance, you have to go through all of her friends before you get to her, right? And so you always want to go to the group that has the least, right? To minimize the steric hindrance. That's going to happen a lot faster than the one that has like 8 girls, right? Okay, makes sense? Okay. Okay, so as the steric hindrance increases, guess what happens? Is it going to go faster or is it going to go slower? Slower, right? Takes longer to get to that on the dance floor because you have to go through 8 girls now instead of just 1, right? Okay. Oh yeah. Oh yeah. Yeah. So I want to go with the one that has 16 people, or I want to go with the one that has 1 person, right? So, with my luck, I always get that one that it has 1 person, but there's a reason why there's only 1 person there, because they have a new employee that doesn't want to do anything. Last time I went to Costco, that's exactly what it was. I'm like, God damn it, this line has gone through 8 people and I'm still going on that 1 person. Okay. So it's all about energy, right? That's what it boils down to, okay? So if we take a look at the methyl bromide, this guy reacting with the hydroxide is lower in energy, gives free energy, than in the case of, particularly in the case of this secondary, right? A secondary bromide. In that case, much more energy associated with it, okay? And so this reaction is going to happen much faster than this reaction. And that's because we have that bigger hump to go through. It's going to take more time to do it. And if you guys remember, there was that whole equation where we can always speed things up with temperature and stuff like that, where it's the activation energy, right? That gap in activation energy plays a part. Well, this guy has a higher activation energy, so it's going to take longer. That rate is going to be longer than this one. Okay. And it also is going to affect the equilibrium, the rate constant. Okay, so if we take a look at this. So both alkaline halides, both are alkaline halides, but they react differently. So in this case, if we have this first hump, this here is going to act as our rate limiting step, right? So because it's the rate to get over it is going to take more time than to get over the next time, right? So this guy will be the rate limiting step, where these two are going to happen so fast relative to this one, okay? So in this case, we're going to get the formation of our carbo-cation intermediate. And we're going to get the separation of the halide ion. And then we're going to get the addition of water being added on, okay? So, but at the end of the day, we're going to end up with exactly the same thing. So starting out with water and our alkaline halide. Same thing, the only thing is that we get the addition, we get the carbo-cation intermediate. So again, first step, longest part. This part is going to be relatively fast, but it still has to happen. And then we'll end up with our product, exact same product, using just water. Okay, so we end up with an alcohol. Okay, so 2 ways of getting from an alkaline halide to an alcohol, right? One using water and one using the hydroxide ion. And you guys know when they say hydroxide ion, what do you think they're going to be using? They need somebody to take it to the party. So what is the most common thing that they're going to be using? What is the most common source of hydroxide, sodium hydroxide, right? So your reaction is probably going to ask you, if you add sodium hydroxide to an alkaline halide, what is going to be your product? Right? So what is going to be your product? An alcohol, right? So if I add water to alkaline halide, what is going to be my product? An alcohol, okay? Which one's going to happen faster? Sodium hydroxide. It is because it's a strong base, so it's causing this gap here is going to be less. And then also it's going to be less. It has a higher gap to get over to this point, but you also have an intermediate that you have to make, and it has a small gap that you have to go over. And then you have another little hump to go over as well, right? So you have 3 humps to go over. This one being the rate limiting, this one is going to take the most time. These are going to be like nothing compared to this, right? Okay. Okay, makes sense? Good. Good. How we doing on time? So 4:24. We'll wrap up here in about 15 minutes. Is that cool? So earlier, although this guy is a primary, this is considered to be a primary halide because the halide is on the main chain, right? At the end of the main chain. This guy's going to act really slow. Why do you think it's going to act really slow? Yeah, because we have these carbons here that are going to act as hindrance, right? So they're going to kind of interfere with that reaction, right? Remember, again, it's going to be reacting on the backhand side, right? So it's not going to be attaching it right here. Well, it's going to be attaching it right here, but you have this guy over here kind of interfering with things. You have all this stuff interfering with things. So it's going to take a little time for it to find the spot that it's supposed to be acting on. We know that we're going to get a reaction occurring on the backhand side. So it's going to be either happening right here, which are both kind of occupied by these other bonds, right? So that they're going to sterically hinder the process. So it's going to take more time for that OH to get there. And if it's water, just imagine how much more time it's going to take because you have a bigger molecule trying to fit into that spot, right? Okay, so we know why it's coming in from the backhand side. So, because we know that it's going to be attacking from the back end, right? So again, carbon, here's our halide. We're always going to get the attacking from this side, right? And then you're going to form your intermediate, right? Where you have your hydroxide actually attached to the carbon at the same time that it's attached to this. Then we're going to get the movement of those electrons to finally release the halide ion. And then we get our alcohol forming, right? So again, if it's an R, it's now going to be an S. Now, depending on what we have, the halide we have, that's also going to affect the reaction, right? So the bigger it is, the easier it's going to get off, right? So if it's a bigger, lower down the periodic table, it's going to be easier to take it off, okay? So the smaller it is, the harder it's going to be taken off because we know that fluorine is so tiny, right? It's going to be harder to get that one to come off entirely. So much that it doesn't actually react. So fluorines are typically not used to form alkaline halides because they kind of suck because you can't get them off. Once you get them on there, they don't want to go off at all. Okay. So iodine If you guys look on your periodic table, iodine is at the bottom compared to bromine, compared to chlorine, and then fluorine is at the top. So in other words, the weaker the base is, since we look at it as a base, right? The better it's going to be at leaving. You know, it's kind of like that. Fluorine is one of those toxic lovers. They don't want to let you go, period, right? Where iodine is like, oh, you want to go? Fine, bye. Don't let the door hit you behind you, right? So it is because fluorine is more electronegative and it wants to keep that attachment as much as it can, right? And the thing is that fluorine is like, you know, I got you. You're mine, period. This electron is really mine. It spends more time with me than anything else, right? And regardless of whether you have somebody else, you're still mine. So it's not going anywhere. So we're going to keep you really tight. Fluorine is really small too, so it really pulls everything really, really tight. So its pull is so much greater. Where bromine has all of those other electrons and then that outer shell, and it has that one that it's sharing, but it's like so far out, it's like, fuck it, you know, bye, you know, oh, well, you're going to give me an electron to go on my way? I'm gone, bye, I don't need you, right? Where, you know, fluorine is so into your business, like you can't separate from them. You can't go potty by yourself and all that. It's just like constantly right there, you know? So. Okay, so we kind of take a look at the relative rates. Okay, so this guy is going to be 1. This guy is going to be 200. This guy is going to be 10,000. This guy is going to be 30,000. So we can clearly see that iodine is like these, you know, where fluorine is like, no, 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 it's not going to happen, right? And then if we look at the Ka associated with that, right? So the Ka values go up, or they go down. The pKa values go down, making the making this guy a lot more. What was that? Acidic, yes, it would be more acidic, making that base more acidic. Is that right? pKa negative. Okay, so this table here is basically a list of all of those nucleophiles. Now, the nucleophiles are going to behave the same way. So if it's whether it's a hydroxide or whether it's a sulfide, they're going to behave the same way, but the rates are going to be different because of the moieties that we have on it. We know that O is more electronegative than S. So it's going to behave differently as a result of that, right? And so we're going to have to take in consideration those things, but the process is going to be similar. Does that make sense? So the rate isn't going to be similar, right? But the process is going to be similar, right? So if whether we're using an OH or we're using an HS, that process is going to be similar. Okay. In terms of similarity, well, this is just listing them, so it's not really necessarily in a specific order. But if we take a look at this, right? So we have these, in all of these cases, they're very similar because they all have hydrogen attached to whatever it is, right? Here we have a hydrocarbon attached to the electronegative moiety, right? Here we have 2 hydrogens attached to the electronegative moiety, right? Here we have a hydrogen and a hydrocarbon attached to the electromoiety, right? And so it's just organized in that fashion. And then I don't know what the hell they were doing here. They just decided to put those all in the same line. So they were just giving a list. There's no rhyme or reason to the list, right? But these are kind of organized that way. So. Okay, so So in other words, you're going to have the base that's going to share its lone pair with a proton, so with an H, right? So the nucleophile shares its lone pair with an atom other than the proton. Okay, these guys are considered to be strong bases, which we already know. These guys are going to be considered to be weak bases. Okay, so these guys are going to be strong bases, so they're going to be better nucleophiles. The reaction is going to happen faster. These guys are going to be weak bases. They're going to be poor nucleophiles. They're going to happen, but we're usually going to need something to kind of help them, right? Help them along the way. Okay. So we kind of saw that with water. It took us forever to get to, well, in theory, if you look at it, there's 3 humps, but it's going to take us forever to get to that alcohol using water compared to using hydroxide. And again, you had mentioned earlier, is because it's a strong base, right? That's happening, right? And it has to do with the fact that in the case of water, even though it's polar, one, you have a charge that's kind of helping things along, right? So in the case of the hydroxide. Okay. So if we take a look at the bases relative to each other, right? Strongest base is going to be the amine ion. This hydroxide ion is going to be the next, and then the fluoride ion is going to be the weakest. Why is the fluoride going to be the weakest in terms of its strength? Because it's like, hey, wait a minute, I got 8 electrons around me. Hell no, I'm not doing it, right? It's like, I got rid of the woman, I got the electron. Okay, I'm good with that now. Good. Sorry, I always relate it to my own relationships. Okay. So polarizable, we also know that it's going to be attacking from which side? What side do we attack from? Backside. So we're always going to be attacking from the backside. Okay, so this is just basically showing us attacking from the backside. Here's iodine attacking from the backside. Okay, so here's fluorine attacking from the backside. Well, iodine is going to end up with more significant bonding because it's so damn fat. It's got more pushing for the cushion, right? It's bigger. So in the case of fluorine is going to be tight. It's going to keep everything very tight. It's not going to want to react, right? So you're going to have very little bonding. So in most cases, you're not going to get the formation of a bond. And if you do get the formation of a bond, it's not going to be as stable exactly as the other. So this guy is going to be considered to be more polarized because you're going to get more interaction that's occurring, where the other guy is not going to get that. You're going to have very little overlap or the share. Okay. So if we start talking about the polarizability versus the nucleophilicity, right? So the question is, or the question that we should be asking ourselves, does the greater polarizability of a large atom make up for its decreased basicity that makes up for them being poor nucleophiles? So the answer is no, right? It doesn't. So, and it says if they're in what was that? protic. So do you guys know what protic mean? Aprotic. Aprotic basically means without hydrogen or without a proton. So if they're an aprotic polar solvent, iodine ion is still the porous nucleophile. And then, but if they're in a polar solvent, a protic polar solvent like water, iodine is now the best nucleophile. Okay. So why is that? And why would the solvent make a fucking difference? Okay, so we had talked about water being a nucleophile itself, right? So was water a weak nucleophile, or was it it was a weak nucleophile, right? And then in that case, the iodine ion would be a better nucleophile because it's a little more attractive. It's going to be more apt to give up the electrons than, than water would be, right? So you're taking the lesser of the two evil. So because iodine is in water, that's a better choice. Where in the case of the aprotic polar, you don't have a hydrogen that's attracting anything, but it's still polar solvent, right? So there's no hydrogen, so you're not getting that hydrogen bonding that would normally occur. So then your aprotic solvent becomes a better nucleophile than the iodine, right? And so it's a competition, right? You have the two things there. You have iodine and the solvent. You could choose the iodine or you could choose the solvent. Well, in the case of if it's in water or in alcohol, then you have that OH, right? You have that H that's going to be affecting things. So that's going to make that a little more attractive, or make the iodine more attractive, because all it is just those free electrons that we're looking at in that case. And you don't have that extra H plus that's adding onto it, right? Where here we don't have that H plus in our aprotic polar solvent. So that's going to be more attractive because that hydrogen is not there to kind of affect what things than the iodine. So it'll be easier to get it from the aprotic polar solvent than the iodine. Does that make sense? Okay, so solvents. So we have three types of solvents. We have non-polar solvents. These are going to be hexenes, benzenes. Okay. We have protic polar solvents. That's going to be like water and alcohols. So those that have hydrogens attached to it. And aprotic, A meaning without, lacking proton. So those solvents that don't have hydrogens attached to an oxygen. Okay. Okay, so let's stop on this one because I think I might remember this slide because of all of the colors. So we're stopping here, slide 27. So when I ask next time, what slide am I on? You guys, slide 27. Yeah, okay. And then on Monday, so Saturday, I'll see you guys Saturday. I'll have labs for you and I'll try to get them out, figure out tonight so that you guys can at least read it. And then we're also going to be making alcohol, right? So yes, we're going to talk about it right now, but we're going to set up for making alcohol. We're going to do the calculations and everything, okay? And then we're going to calculate how much alcohol percent that we want. And then we're going to calculate, because we're going to do a little bit better than what we did in 2A or 1B, right? You guys didn't get it, but they did, sort of. How did yours turn out? Have you? Your wine, yeah.
Good. What time do we come on Saturday?
At 9 in the morning.
Ah.
Yeah. Okay.
And then is homework 3 going to be extended?
Yes,
Or...
I'm extending homework
okay.
3, and I'm going to add on some some more questions. And then I'm going to be putting up more attempts, yes, not more questions. And then I'm going to be putting up homework 4. So, yeah. And then also next week, your exam is going to be opening up. Okay. So it's going to open up, yeah, Friday, not this Friday, right? Next Friday. It's going to open up next Friday. So you have plenty of time to sit there and think about it and stress over it and everything like that. But it's only going to cover, chapter 8. Okay. So yes, you'll have a week to get it done. So it'll open up on Friday and it'll close on Friday. So yes, the practice test will be up. It's not up yet. It will be up on Friday. It'll open the same time when the exam opens. So you'll have. I will try to have it open up before the exam, but you'll have a week to get it done. So you'll have a week to practice, right? Okay. I'll try. Yeah. Okay. Okay. But chapter 9 so far, I have to admit, chapter 9 is so much easier than all the shit that we've done in the past. I mean, is it just me? Is it just me, or is it, yeah. Because that's because we're starting to get, but we're starting to piece together. Okay, so these are the things that we can say. Okay, so these are all going to be nucleophiles. And so things are getting a little more organized, Yeah. At least that's the way I feel. And it's funny because it's like somebody else wrote this part of the book. The first 8 chapters, I don't know who in the hell wrote it, but they were like smoking something, I'm like, man, they were like, I don't know, but it felt like to me, and as the instructor, I felt like I was going here, and then I was going here, and I was going here. And I'm like, I don't understand why they're trying to take us down these paths, and I don't see how it's all converging together. I know in terms of this is how they typically teach organic chemistry, is that they start with the alkanes, then they go with the alkenes, and then they go with the alkynes. Man, they were just going so many different directions, and nothing was like a straight path, so. And now this is making a little more, to me, logistically, it's making more sense. Okay, I will see you guys. Okay, so let's talk shop. Can we take a 10-minute break? I need to go grab some water because my throat is kind of killing me. And then what we'll do, we'll work out some calculations to try to figure out how much sugar we need to be adding, and then our alcohol content and all of that stuff, what we're expecting. And then we'll talk about timelines, because our goal is to get enough alcohol to reach our maximum alcohol potential. We're going to half the liter, we're going to save for, let's say wine or whatever, we'll say half of the 2 liter. You're going to save for wine, and then the other half you're going to save for alcohol production. Okay. And yes, for you. Yes, we'll talk about that after, if that's okay. Yes. So you guys need to finish your lab. Okay. Okay. So can we talk shop first, and then we'll finish the lab? Okay. So let me go grab some water, and then. Okay. How are you guys doing? I think it's. So it's just me. Yeah. So, okay. So let's talk shop. Okay. So what we're going to be doing is I'm actually changing my mind here. So you guys are going to be doing 5 gallons. 5 gallons, yeah. Okay. So you guys are going to do your normal groups. You guys typically do in groups of 3 or 2 groups? 2 groups? Okay, so we'll keep you guys in 2 groups. So we'll do 2 5-gallon jugs, 2 big 5-gallon. So I'll be sure to I bring enough, you know. Okay, so if we're going to assume that we're trying to get 20% alcohol, that's our goal. And we know that the chemical equation for the production of alcohol is C12, assuming we're using sucrose, H22O11, and then that's going to give us CO2 plus C2H5OH. Okay, so we need to balance out the chemical equation. I'll let you guys work on that while I look pretty. So how do I do that? Actually, let me revise the equation to make it a little more palatable, because really what happens is this. Your sucrose gets turned into glucose. And then we'll do the equation for the transition from sucrose to glucose. So then that's 12. Oops. Sorry. Okay. Oops, let me fix this. So you said 2, 2, and 2? Okay. So then that, sure, let's see, that's 4. That's 6. It's 12. Oh, 6 and 6. Yeah. Okay. Okay. So if we want 20% alcohol of a 5-gallon tank, right? So 20% by weight. So, and we assume that we're saying 20%. 20% of it has to be alcohol, and that means 80% of it is going to be water. So we know that the density of that is going to be roughly the density of water, right? Because clear on that? So then calculate how much sucrose am I going to need for a 5-gallon reaction. So our goal percent alcohol. Of a 5-gallon reactor. Okay. So then how much glucose do I need to start off with? What more do I need to give you? Assuming the (20% alcohol solution is the density of water. Although I should make you guys, because you guys at this point should be able to use things that you've learned in the past to calculate the actual density of 20% of water. But I won't in this case. Then you off easy. That's what we're working on. I would write it on a separate piece of paper because you guys are working out the protocol. Okay. And since we're only going to have 2 groups, we're going to make wines that I want. So one is going to be strawberry hibiscus, bomb ass wine. And I think the other one is going to be, don't get creative. You will get creative. I think I'm going to do blueberry. Blueberry is a pretty good wine. Blackberry was a pretty good wine too. So, or mango. Mango was really good. Maybe I'll do mango. I have to see what's available at the supermarket. I should say, that's cheap and available at the supermarket. So if it's 20%, we're assuming it's 20% volume roughly, right? So if we assume 20% volume of water, then we're talking about a 5-gallon total volume that we're working with. So then we're looking at 5 gallons, whatever 5 gallons was, then we'd use that value to calculate how much alcohol, the mass of alcohol that we're making, right? Or that how much we want to make. I'm not answering your question because you're looking at it crazy. Okay. Okay. So if we assume that the density of 20% alcohol is going to be the same as water, so it's just 1, yeah. Okay. So then we're able to get the mass of both the alcohol and the water that we want, right? Okay. So in actuality, the density of 20%, well, the density of alcohol is 0.79. So if you assume that if we had 100 grams, 20 grams was alcohol, then you multiply that by 0.789, and then that would give me the number of grams I have in theory. But I said just assume that it's water, right? Because water technically weighs more than alcohol per milliliter. So we'll have excess. We'll have a little bit more if we use water in that theory. Does that make sense? How long are you guys going to need to finish your So what did you guys get? Have you guys got an answer? So what would be 20% of 5 gallons? 1 gallon, right? And we know that 1 gallon, if we converted that to liters, that's going to be 3.79, okay? So 3.79 liters. So I need to change liters to milliliters. So then that'll be 3,700, okay? Okay. And you said you got 3,789.85, okay? Grams, right? Because if we made the assumption that the density of 20% is about 1, right? Okay, so that means that maximally we're going to be adding 3,785 grams. How many pounds is that? Pounds of sugar. I would have changed that to pounds. 8.33, 8.34 pounds. Okay. So we need at least 8.34 pounds of sugar. Okay. Oh, sorry, not of sugar. That would be of alcohol. So we got to change that alcohol to. So what is the ratio? The molar ratio. We have to change that to moles. And then we got to convert to how much sugar we need. So we're going to end up with 8.34 pounds of alcohol. Got carried away. So if I wanted to figure out how much sugar I need, so then I need to change my alcohol by using its molar mass. Was that 46? 46 grams per mole. And then we use the stoichiometry. 2 to 1. Mole divided by mass of sugar. 1. You got 6 pounds? I got more than 6 pounds. I could be wrong though. I mean, I'm not gonna. I just did it real quick in my head, so